In part 2 of this video series, we will be looking at the sinusoidal steady state analysis, and just to be clear that every complete response of an electric circuit is composed of two parts, the natural response and the force response. We are only concerned with the force response. The natural response or the transient response you will see in another course, maybe circuit analysis. But for a short intro of what natural response is, that whenever some switch is flicked, or whenever some voltage source is connected to a circuit, we have a little bit of transients, and then those transients die out, and what remains is something known as a steady state. You might have noticed that whenever you turn on a heavy inductive load in your house, such as the motor for the water pump or the air conditioner, if you turn that on, you might have noticed that the lights flicker for a few seconds, and then everything gets back to normal, because the electromagnetic field requires a large amount of current to build up in that inductive load. It requires a huge current to build up that field, and then when the field is made up, the everything returns back to normal. So the very small phase or very small time period in which the transients or some temporary stuff happens, that is known as natural response, and whenever everything gets back to normal and everything is running smoothly, we call that state steady state. So we are only concerned with the force response here, not natural response. So we have seen in part 1 that what sinusoids are written as. Sinusoid means sine or cosine, which I'm going to explain in part 3, and they have it's a form of the magnitude. Let's say it's a voltage Vm sin omega t or Vm cos omega t. That's the amplitude Vm, argument is omega t, that is the radiant frequency, which I've explained that. So if we just plot this thing in terms of t, so it's in terms of time period. So here we have a sine wave of half time period, that is 0, and so on and so forth. You can also represent that as a function of omega t, but here you are writing the angles in radians. And frequency, I've just explained that omega equals to 2 pi f. Another concept we need to keep in mind is that general form of a sinusoid is sine omega t plus theta. This thing is given in degrees and this thing is given in radians. And if I plot this thing, Vm sine omega t, and the original function sine omega t, then we can this is the green wave, and if we plot this thing sine omega t plus theta, that is this red wave. So this thing, if we put t equals to 0, sine has an angle. Okay, so that it has some angle, and that is represented by theta. So this starts at not at 0 but sine of some number. So here if we have if we put t equals to 0, sine is going to be 0, so that is going to be this green wave here. So here this thing, the phase angle is included in this thing, and we can say that this red wave is leading the green wave, the green sine wave, by theta. Okay, here it's given in radians, but actually in traditionally electrical engineering, phase angle is commonly given in degrees, not in radians. So we should be writing, instead of radians, we should be given in degrees. Okay, and this 2 pi ft means 2 pi f that's 1000, and it's a time domain function. If you put value for t equals to 0, that will be 100 sine minus 30. If I put t equals to 0.1, that will be 100 sine 2 pi 1000 into 0.1 minus 30. So for different points in time, we can plot the instantaneous values for this function v. So we can say that this red wave is leading the green wave by theta. If it's given in degrees, so we can say theta degrees, or we can say that this green wave is lagging the red wave by theta degrees. Now what we have to do is, whenever you want to compare the two sine waves whose phases are to be compared, they have to be written either both in sine or both as cosine. We will be using simple cosines because the reason is that is the real part of the Euler's identity. So we will be, sine and cosine are essentially two parts of the same picture. I'm going to explain that in part 3. But you have to write this thing either in sine or in cosine, and both must be written with positive amplitudes, and each must have the frequency. So if you want to convert sine into cos, so you have to subtract 90 degrees. Okay, so next thing is that if we have a simple RL circuit, and we have a sinusoidal forcing function or sinusoidal source or sinusoidal excitation, three names for the same thing. It's a voltage source, and if I want to figure out what is the value for this current I, and let's say we do not use the phasor analysis which you have seen in some other videos. So let's say if I write a simple KVL equation, what would that be? I can write the source. I'm going to write going from starting here and ending here, simple loop equation. I'm going to write minus, so I'm counting the minus sign first, minus Vs plus Vr plus VL equals to 0. So I can write this Vs on the right hand side, so I can have Vr plus VL equals to the source voltage. So if I write this, I mean, we know that voltage of resistor is equals to IR. So I can write IR here, and we know that the voltage of this inductor is defined by the equation VL equals to LdI over dt. So if I write this thing as the source voltage equals to VL plus VR, so instead of writing VR we write RI, and instead of writing VL, the voltage of inductor, V subscript L actually, so I can write LdI over dt. Now if I know this has become a differential equation, first order differential equation, and to solve this thing we have to figure out a function which satisfies this equation. So we need to figure out the expression for I which satisfies this equation, and then that would be the solution for this differential equation. So we have several walkarounds how to figure out. Let's say we assume that the form of the solution is I1 cos omega t plus I2 sin omega t, and if we put the value just to check whether this thing is actually valid and collect the sine and cosine terms and then solve the equation, which you might have done in your differential equation course, you end up with I1 and I2, and the complete response or the force response has to be this complicated looking term. Then we can, this is all time domain analysis, but here we have the alternative form of this IT, Vm over R square, and this is a very large equation, but actually this is, if you look it closely, we are just dividing this thing by the impedances of the resistor and the inductor here, but we cannot use the word impedance in time domain, but that is actually behind the scenes story, that whenever we are performing the frequency domain analysis, some similar things are happening in time domain, but with a different numbers or different values, and giving a phase shift to the cosine function here. But here, since we are doing the time domain analysis, we are writing R square and this omega square and L square. This thing is given in henries, this thing is given in radians, and this thing is given in ohms, and we are providing some kind of a phase shift to this cosine function. So you might have seen, you might have noticed that performing the time domain analysis is actually doable if you have a differential equation. Had there been a capacitor, that would have been the capacitor is IC equals to C dV over dt, or integral I dt, that would have been the value for the voltage for the capacitor, and that would have become the integral equation, and then we could have taken the differential to cancel out the integral, and that would have still become the differential equation. But you might have noticed that this is actually quite a cumbersome and a difficult way to solve a simple problem. So instead of doing the time domain analysis, which we have just seen, and to solve the differential equation, we use something known as phasors. Okay, and these phasors are actually frequency domain quantities, or actually what we do here is, I'm going to explain that in part 3 of this video series.